Welcome to our Warsaw University Tuesday seminar series. Welcome in 2022 to this first seminar this year. And today our speaker is Krystian Iłkiewicz, who is our graduate. Here. And then we have attorneys at Warsaw, and then abroad, US, UK. Now he's back again with us, and then he's not spoken with the local research here. And just a reminder, your masks.
Hello, thank you. First of all, let me thank everybody for welcoming me here after so many years of being away. And it's a pleasure to come back and be again in this room. So the topic of my talk is accretion processes in cataclysmic variables. So I know there are few students in the audience. It stopped working. Łukasz. Okay. Thank you. So as a short reminder, what is a cataclysmic variable? Cataclysmic variable is a binary star where we have main sequence star that is transferring mass onto a white dwarf. The accretion is usually, but not always, to accretion disk, and where the accretion stream hits the accretion disk, we observe a hotspot. So why study accretion? It is one of the most important phenomena known in astrophysics, and it governs the evolution of basically everything that we see on the sky, from young stellar objects to AGNs. It is also important for our understanding of things like supernova 1A progenitors and gravitational wave sources. And this is the main reason I got interested in this topic. I was doing population synthesis studies of supernova 1A progenitors, and I had to put a number on how efficient accretion is in my systems. And the number was an educated guess, and I didn't have much confidence in it. And for this reason, I decided to study accretion and give myself better confidence in my numbers. And although it is so important to understanding almost everything in the universe, there are still many unsolved mysteries about accretion. There are still unanswered questions and still new surprises to be found. So this is worrying, given how important it is that there are so many unsolved questions. But why study accretion in cataclysmic variables in particular? First of all, they have wide range of mass transfer rates. So we can study accretion in many different environments and build models based on that. So they are well grounded in a wide range of parameters. And the other reason is that we have a white dwarf, which is pretty low massive star. And we don't have any gravitational general relativity effects. So our models can be pretty simple. We can build simple models without general relativity and then apply and evolve these models in more complicated situations like accretion onto black holes in AGNs. So I said to you there are many surprises to be had and many unsolved questions. So I will give you one example that I found with my group, that my group found, my previous group in my previous postdoc last year. And the surprise was about low states in cataclysmic variables. So what are low states in cataclysmic variables? So they come in many shapes and sizes, but the basic idea is that we have a drop in the brightness of the system by a few magnitudes, and the drop takes pretty long time, at least 10 days in the fastest systems, but in some systems the drop in magnitude can take at least months. And while we are in the low state, almost nothing happens. The light curve is pretty flat. And the transition back to the bright state takes almost the same time as transition into the low state. So it's pretty symmetrical effect. And this effect is well known and studied for many years. And it was explained by gradual decrease in the mass transfer rate from the mass donor, so the main sequence star, to the white dwarf. So simply the main sequence star gives less mass to the white dwarf, so the magnitude drops. It's a very simple process, you would think. But the surprise came when we looked at test data of a cataclysmic variable TWP. So here you can see the low state. And what is surprising about this system is that the drop to the low state took only 30 minutes. So previously we needed, in all other systems with low states, we needed at least 10 days. And in this system, it took less than 30 minutes. And the change from the low state to bright state took longer, 1 day, more or less. So it was much longer, but still much shorter than all other low states, other cataclysmic variables. So to reiterate, in previously known systems, the transition was very long, at least 10 days. In TWP, it's very fast, on order of 30 minutes. So it may suggest that TWP is more similar to transitional millisecond pulsars, where there are similar switches between high state and low state, but the switch from bright state to low state takes only 10 seconds. And the way TWP is similar is in that the drop from the high state to low state is very fast, but from low state to high state is significantly longer. So what may be the physical reason behind that low state? We already know it is not the same as previously, because such dramatic change in mass transfer rate cannot simply happen because the mass donor stopped the mass transfer so abruptly. So the reason has to be different. And the hint comes from the variability during the low state. So we see many flares separated by roughly 2 hours, and each flare lasts for about half an hour. So we interpreted in our paper these flares as magnetically gated bursts. So the idea behind magnetic gating is pretty simple to understand. So this is a short cartoon illustrating that. We have magnetic field that acts as a gate. It prevents the matter to transferring onto the white dwarf. So the matter builds up even more, and it pushes with more pressure on the magnetosphere until the magnetosphere gives up and lets the mass through. And when the mass went through onto the white dwarf, we see a flare. The system brightens up. And then all the mass in the accretion disk went onto the white dwarf. There is no mass left to push onto the magnetic field, so the gate closes. So to put that into more physical terms, here is an illustration of the process. On the left side, you see a panel during the lowest state, so outside of the flare. And on the right side is the state of the system during the flare. So concentrating on the left panel, we see that the accretion disk innermost radius is farther away than the corrotation radius. And the magnetosphere corrotates with the white dwarf, and white dwarf rotates too fast for the accretion, for the matter to in the accretion disk to fall onto white dwarf. So the Keplerian velocity of the matter in the innermost radius of the accretion disk is too slow to keep up with the white dwarf. So the magnetic field pushes away the matter. But when we build up enough pressure in the accretion disk, we shrink the magnetosphere and we move to the right-hand side panel. So the innermost accretion disk radius is closer to the white dwarf than the corrotation radius. So the matter in the accretion disk rotates fast enough, and it can accrete onto the white dwarf. And we see mass going onto the white dwarf and a flare. So basically, the the thing governing the flares and the low state could be just the innermost radius and co-rotation radius relation, and where is innermost radius governed by the magnetic field and the pressure from the accretion disk. So the very fast transition into the low state could be explained by a very small change in mass transfer rate, because we just don't need to turn off the mass transfer rate completely. We just need to decrease it slightly, so this can be done very fast, just so that the innermost radius moves outside of the co-rotation radius. So the small change in mass transfer rate that could happen very fast could give us a response from the magnetosphere, which could give us a very big difference in brightness. So this was the surprise from the last year that no one expected. So I hope I convinced you there are many things to discover in accretion processes in cataclysmic variables. So moving forward to my current work here, I am studying cataclysmic variables with TESS. Currently, my sample has over 300 objects, but this year probably will expand to 500 objects. And TESS is very nice to study cataclysmic variables because the cadence of data is about 2 minutes for most of the objects, and sometimes we even have cadence of 20 seconds. And typically, one object is observed for 28 days, almost continuously, and the orbital periods of cataclysmic variables are less than 1 day. So you have very good statistic on any variability related to orbital motion. The orbital motion is covered by many times during one observation series. So we can make very good statistics on the orbital variability, and this is what I'm mainly interested in. And this is an example, part of the light curve of TESS of one of cataclysmic variables, namely AQMan. So as you can see, the data is not amazing, the errors are pretty big. But when we zoom out, we can see we cover many orbital phases, and if you zoom out even more, we can see that we cover huge amounts of orbital phases. So we can make a phase plot of orbital variability and calculate the mean orbital variability seen here in a black line. And around the black line is a gray area that you maybe are not seeing because it's so small. So the error of our mean orbital variability is tiny. So we can study everything in great detail and look at everything very sharply. And this particular system is very interesting to me. It piqued my interest when I first went to test data because the eclipse is very shallow. Usually, you expect the eclipses to be very deep, but here it's exceptionally tiny. And this is because the system looks like that. It's inclined to us. So the eclipse is not of the white dwarf. It's only of the part of the accretion disk. So because the eclipse only grazes the accretion disk, the flux changes slightly. So because we eclipse only very small part of the accretion disk, not the full accretion disk. And this is called grazing eclipses. So they are not seen very often, they are pretty rare, but when we see them, they are pretty cool. And in particular, in AQMan, they are cool because when you look again at the zoomed out picture of the whole light curve, you see additional variability that is on a much longer time scale than the orbital variability. And this is how it looks like when you make phase plot of this additional variability. It is called actually superorbital variability. Superorbital because the periods are much longer than the orbital periods. So that's where the name superorbital comes from. And as you can see, it looks pretty sinusoidal. So it is actually this kind of variability known for many years. I think 40 years or something like that. But we still don't have definite proof of the nature of the superorbital variability. So it's interesting to look more into that. And the most prevalent theoretical explanation of the superorbital variability is that the accretion disk is tilted. So it's not in the orbital plane of the binary. And the superorbital period is actually the period of the precession of the accretion disk. That's why it looks sinusoidal and it's much longer than the orbital period. So this is the most prevalent theory at the moment, but there is no definite proof of this theory. And that's what I wanted to prove with this object, this theory, that the accretion disk is tilted. And accretion disks that are tilted are not only being theorized to exist in cataclysmic variables, but also in X-ray binaries. So this is something that can apply to a wider range of astrophysics than just cataclysmic variables. So it's an interesting topic. So again, we have grazing eclipses, but we also have superorbital variability. So the picture actually looks like that. We have grazing eclipses of precessing accretion disk. So when you imagine that process, when you have precessing disk at different period than the orbital period, each eclipse should look different because each time there is an eclipse, the precession of accretion disk is a different phase. So it's oriented differently towards us. So each eclipse for each different superorbital phase should look different. And this is what I was looking for in IQman. So here is the same phase plot of orbital variability, but what is different now is that with color, I mark different superorbital phases. So each color corresponds to different orientation of the accretion disk that was predicted by the theory that I was checking. And when we zoom into the eclipses, actually we see that for each phase, the eclipse is slightly different. And this is more quantitative way of showing that. On x-axis, we have superorbital phase. So the phase of the precessing of the accretion disk, and on y-axis, we see how big was the eclipse at every phase. And we can see there is a maximum and there is a minimum there. So this is the first direct observation that proves that the accretion disk can be tilted. And this is, I think, pretty important discovery because this is not intuitive, that the accretion disk can be outside of the, not in the orbital plane. And IQman showed direct observation that was predicted by theory that this happens. So for the first time, it is a direct proof of this theory. So this is what I published last year. So I will show you what I am working on about IQman and this tilted accretion disk in the future, future work. So here is a plot showing you these angles, what I call this angle, and this is basically the angle between accretion disk and the orbital plane. So it is exactly saying how far out of the orbital plane is the accretion disk. And on this axis is a unitless way of measuring the period of the superorbital variability. And what Montgomery predicted is that there is a relation. This relation is different for different mass ratios, but there is a relation. And what is particularly interesting about IQman is that we showed that this period changed from 2002 to 2018. It changed dramatically, which would indicate that the accretion disk angle out of the orbital plane changed with time. So this is the prediction made by Montgomery. And I particularly hate this prediction because you can see in 2002, it indicates that the disk is 50 degrees outside of the orbital plane. And this I cannot believe. And of course, this depends on different system parameters, like in particular mass ratio. But in order to be consistent with the same system parameters in 2002 and 2018, changing only the disk angle, this is the lowest that we can get for 2002. There is no way to get a lower value for 2002 by not excluding the observation from 2018. So I wanted to really check whether we can measure directly how far out of the orbital plane is the accretion disk. And actually, this figure is from a program that I wrote that calculates some system parameters, puts in precession of the accretion disk, and measure how deep are eclipses. So it's a very simple program. And here is an example plot from this program. This is the simple example. You can see disk angle is 0 degrees. So the disk is in the orbital plane, the simplest case possible. And top panel shows you how the eclipse depth changes depending on the superorbital phase. So how it changes depending on the phase of precession of accretion disk. And the lower panel shows you the superorbital variability. And of course, here the disk is inside the orbital plane, so there is no superorbital variability. But when we put the disk outside of the eclipse plane slightly, we can see superorbital variability develop, and you can see some variability in the eclipse depth. And this particular example is for my educated guesses of AQMan orbital parameters. And as you can see, the depth of the eclipse, the highest depth of the eclipse is not very deep, and it's very narrow when we see this effect. But when we change the disk angle to 10 degrees, the effect lasts for much longer, and the eclipses are much deeper. So I made a more quantitative plot. Here is a disk angle again, so how far the disk is outside of the orbital plane. And on the y-axis is the eclipse depth that we predict. Red line is the maximum eclipse depth that we expect. And black line is the median value across all superorbital phases. And you can see that the relationship is quite sharp. So hopefully in the future we can use that to measure directly the disk angle. But I would like more AQMan data to do that, because I would need to observe the change in the angle to be really sure that this is due to this effect. So moving forward to the work that I will do here in Warsaw, in Observatory, I will study, first of all, flickering. So what is flickering? Flickering is simply a stochastic variability that is observed on all time scales, from gigahertz to years. And it's always associated with accretion. So when we see flickering, we know that there is accretion, and when we know that there is accretion, we know that there will be flickering. So it's always connected, accretion and flickering. That's why it's interesting for studying accretion. The actual physical origin of flickering is not known. We have no idea. There are a few models, but absolutely nothing confirmed, only wild guesses. The only thing that we know about the physical origin of flickering is that it is due to multiplicative process and not additive process. And we know that because the distribution of fluxes is log normal. So this is the only thing that we have, but it cannot pinpoint the exact model of flickering. Not any old noise is flickering, and flickering is recognized by two main features. So if you see noise, it not necessarily is flickering, but if you see these two features, it's certainly flickering. First of all, when you calculate power spectral density shape, it is explained, described by a broken power, always. And there is also a relationship between the amplitude of the flickering and the mean flux of the system. And this is a linear relationship. So this is how typical flickering looks like. As you can see, it looks like noise, just random flares with random amplitudes at random times. So stochastic process. And this is how the amplitude mean brightness relationship looks like. And you can see it's very simple, straight relationship between the mean flux and the RMS. So RMS, speaking differently, is the amplitude of flickering. And this is the power spectral density of data showing flickering. And you can see the break frequency at frequency of 10 to minus 4.26 hertz. So this break frequency actually was studied in detail, and the empirical prescription saying to us how big it should, where it should be. So here is a plot where the y-axis is the actual observed break frequency from real observations, and x-axis is the predicted one. So how we predict that? We take out the system, we just assume that the break frequency is a linear function of mass of the accreting object, mass accretion rate, and radius of the accreting object. And when we feed the coefficients to all the data, we see that it feeds the same coefficients feed every object that we study, from young stellar objects through cataclysmic variables, through X-ray binaries until AGNs. And based on that, Scaringi in 2015 claimed that flickering has the same physical source in all accreting objects. And by all, I mean everything with accretion. And I really hated that statement in this paper. And that's why I did my postdoc with Scaringi as my boss. And I tried to prove him that he was wrong. So I studied flickering in polars. So polars are cataclysmic variables with strong magnetic fields. So the magnetic field is so strong that it prevents formation of accretion disks. So the accretion is through magnetic field lines. And I studied flickering in polars because, in my personal opinion, this is the hardest object to find a physical process that is the same as in all the other accreting objects. So YSOs and AGNs, I don't see how you can connect that objects with polars. And this is the hardest part for claim made by Scaringi to explain. So how I study flickering in TESS data, I find any polar that has pretty stable light curve. So where we can see orbital variability, but no long-term variability. And if there is any long-term variability due to secular changes in the telescope or something like that, I just flatten it out. So the more flat light curve that is more flat, better for me. Then I make a phase plot. So this is how it looks like. The gray points are the TESS observation, and the black line is the mean orbital variability. I then subtract the mean orbital variability and make a flat plot where gray line just represents the scatter in data. So the scatter in data, how big was the scatter in data indicates how big was the amplitude of flickering and certain orbital phases. So then I bin this data and measure the root mean square. So here in black is just the changes of flux with the orbital phase, and in red the changes in RMS with the orbital phase. So this is equivalent to changes in the amplitude of flickering. So why did I do that? Because I want to find out where those flickering originate. Because if we know exactly where in the system the flickering originates, we can develop theoretical models that contain the whole physics in this region. So this is a zoom in on the accretion column when it hits the white dwarf. And looking from the top, we have accretion column coming onto white dwarf surface, and on the top we have a cool supersonic accretion flow. So it is actually pretty fast and pretty cool matter. It's going fast, but right at the bottom we have a white dwarf surface. So we know the matter has to stop there. Right above the white dwarf surface, we have a hot subsonic settling flow. So this is like a traffic jam of the particles that want to get onto the white dwarf surface. They have to slow down, they cool down in the process. So it's a pretty complicated process as well. And we have shock in between this fast matter and slowing down matter. They collide, and this creates a shock. So this is also pretty stochastic process. So all these things, except maybe cool supersonic accretion flow, can be a source of flickering, because out there we can imagine stochastic processes going on that give pretty big amplitude. So these are our educated guesses where the flickering can originate from in polars. So what Bruch published last year is shown here. Top panel is just the orbital variability of one of the polars in their data. So it's a typical variability for polar. And on the bottom is the change of the amplitude of flickering. And here we can see that the maximum amplitude of flickering happens exactly at the same time as the maximum of the orbital variability, so the maximum light coming to us, and the same for the minimum. They happen almost at the same time for the flickering and the brightness of the system. And the same I observed for many of my polars. So previously, similar thing was only done for one object, but I see the same for many of my polars. And based on that, what Bruch suggested is that the flickering originates at the bottom of the accretion flow, because this is where the white dwarf gets heats up. So the main source of light in the system. So it makes since the flickering amplitude and the light and the brightness are correlated, this suggests that the physical place where they originate is the same. And as I said, I observed the same in many other object polars. Here is an example of one of these polars. We look at the same exact polar, but later we see the situation changes slightly, but okay, the image is more or less the same, but we move forward 100 days and we see something dramatically different. First of all, in this polar, at some point, new eclipse occurred that is very shallow. So some people may be wondering how we can develop new eclipses where there were none before. And this is because usually in binary stars, the eclipse is by the one of the stars. So in cataclysmic variable, it is eclipsed, but the eclipse is usually by the main sequence star, but not here. Instead, the eclipse was by the accretion stream itself. An accretion stream can change its geometry very fast. You just need slight change in mass transfer rate and can change the geometry significantly. So the eclipse was not by the main sequence star, but by the accretion stream. So that's how it could develop. So where we see the eclipse, new eclipse, we also see eclipse in the flickering source. So the amplitude of flickering drops down. This is what we expect if what Bruch said is true. that the light and the flickering originate in the same place. But we see different eclipse that happens before. So since this, before the new eclipse, so this eclipse happens only in flickering. So now this suggests that we have a confined source of flickering that is different from the main source of light. So this is something completely new. And the same is seen in other objects, for example, here, where there is completely no eclipse of the light, of the mean brightness, but there is an eclipse of the amplitude of flickering. And here is also very interesting case. The light curve is slightly different because we have two poles. So we see during one orbital phase two brightenings because here the accretion is onto two poles. We see a plateau between them, but also we see a deep eclipse that this time is due to main sequence star. So even though the light source is eclipsed completely, the flickering is not eclipsed at all. So this is even more confusing. So basically, what we see from TESS is the flickering source is not only the photosphere of the white dwarf, it also has to originate somewhere else. And because the eclipse time is different, we know it has to be far away from the white dwarf surface. And another proof of that is the relation between the flickering amplitude and the mean brightness. Here is the plot that I showed you before, how it should look like. And here is the same for one of my colors. So x-axis is the flux, y-axis is the RMS, so the flickering amplitude in different words, and with color is different orbital phase. So actually what we see here is two different RMS flux relations. So again, this confirms that we probably see two sources of flickering. And my favorite theory is that this flickering originates in the shock. And I don't think it originates in the supersonic accretion flow because this is too quiet. The accretion stream is too quiet. And at least in my simplified picture, I don't see any stochastic processes with this big amplitude happening there. And I don't also like hot subsonic settling flow, even though it's very stochastic region. We actually know that there are quasi-periodic oscillations happening there. So we know that this region produces variability on that is quasi-periodic and on much faster time scales than I observed here. So this region, hot subsonic settling flow, produces variability on time scale of 10 seconds or even faster. So the same similar picture actually I saw before in symbiotic stars. So symbiotic stars are similar to cataclysmic variables, except the mass donor is red giant, not main sequence star, and accretion is usually through wind accretion. And what I saw a few years ago, you can see here, this is X-ray light curve. The red points and red line are observations between 2 and 5 kiloelectronvolts, so pretty soft X-rays. The blue is between 10 and 15 kiloelectronvolts, so pretty hard X-rays. And green is in between, so 5 to 10 kiloelectronvolts. And what I saw a few years ago is that sometimes we have flares that can happen in all bands. Sometimes in some bands, the flares are faster and in some later. And sometimes we see anti-correlation. So here you can see anti-correlation between the green and blue. So the very hard and not so hard X-rays. And sometimes there is no correlation at all. It's completely chaotic. And actually in this system, the hard X-rays are from the boundary layer between accretion disk and the white dwarf surface. And the soft ones are from the colliding wind regions. So these are completely disconnected physically. They are very far away. And because we see sometimes correlation between them, sometimes anti-correlation, I suggested years ago that there are many different physical origins of flickering, but my previous boss or my postdoc didn't believe me then, so hopefully I will convince him using polars. So let's move back to normal cataclysmic variables with low magnetic fields. So pay attention to the hotspot, because this is very interesting feature in cataclysmic variables. We should in principle see it in all cataclysmic variables with accretion disks. And the hotspot looks like that during the orbital variability. It just shows as a bump somewhere during the orbital period. So before there is a plateau, and at some points there is a bump. So that's why we say hotspot bump sometimes in papers. But sometimes you don't see any. In some systems, you don't see any hotspot, and this is maybe something we wouldn't expect. But maybe we can use flickering using the same method as before for polars to see whether we can find the hotspot hidden somewhere in there. So for this exact system, where we measure the flickering in the exact same way, so again, with red is the amplitude of flickering, we see there is a hotspot-like bump before the eclipse. And looking at different system, we see that there is hotspot-like bump after the eclipse. So maybe flickering can also help us find hotspots in systems where we don't see any hotspots in just simply looking at the orbital variability. And there are some mysterious systems in my sample as well. So this is pretty funny looking orbital variability. Namely, we see, depends on how you interpret that, either two eclipses or one long eclipse with a bump inside it. So when we, again, using the same methodology, look at the flickering in the system, we see that only one of these eclipses corresponds to the eclipse in flickering source. And this is non-magnetic system. And I have no idea how to interpret this data. So if you have any ideas what can cause that, please let me know. As a conclusion, TESS is very fun to study cataclysmic variables with. Especially, I like the flickering and the different aspects of orbital variability. And last second of my talk, I will use for advertisement. If you are a student, I am new here and I am looking for students, and I have 1 year funding for either a bachelor of thesis or master thesis. So if any of the topics got you interested, please talk to me later. Okay. Thank you.
Thank you very much. Krystian, are there any questions here from the audience first?
Can I start?
If you could come forward because the microphone is not here.
Okay. So I just wanted to say that the presentation was very interesting and very creatively presented by various pictures. And my question is about the Montgomery relation. Because it was a single line, I just wanted to ask, like, how and compared to the data, like how confident can we be that it like precisely or accurately describes like the processes that we are looking into?
So we cannot be sure at all. I don't personally believe at all in this. So this is one line, but as I said, this depends on the system parameters. So here I guess equipment parameters. I make an educated guess and I put that into the model, and this is the line I got. I can give you a line that is higher or a line that is lower, mainly depends on the mass ratio. So I just put one mass ratio that I chose, and this is the line that I get. So you can play around with it, make it go lower or higher. But this one particular I chose is because it's consistent. It's consistent with observations with these 2 years, and it doesn't give angle of 90 degrees. Accretion.
Thank you.
So this is purely theoretical, depending on that. Don't believe it.
Okay, thank you.
So since you're just a follow-up question, since you're on this plot, you said that the degree is how far this tilts from the plane, but then 0 means it's completely aligned.
Yes.
Right. So why there is, or maybe it's not shown here, but for 0, as your simulation showed, there should be no superorbital period.
It's a philosophical question. Maybe there is, but you don't see it.
But then
because the amplitude goes to in infinity when it asymptotically to 0.
Sure, but I don't understand this plot there. So for 0, what's the value on the y-axis?
You have certain period, but you don't see this period because the amplitude is 0. So as I said, this is a theoretical model that I don't.
Right, because then you said you changed just 5 degrees, which is not far, not much far from this, and you already get C5.
Yes.
Right? So then I understand this. And then I would expect it drops.
Yes.
If this is the period, not the amplitude, then I agree. Well, I understand. Okay, thank you. Nana. If you could come forward because the microphone is.
It's also related to this. So my question is, I understand there is this angle, right? But why? How does it occur?
Exactly the right question that we don't know the answer to. And there are many models. One of the models says that I like that when you have accretion stream, it goes under the disk and pushes the disk outside of the orbital plane. What I like as an explanation, that is my not published anywhere, is that because between 2002 and 2018 there was a low phase in the system, so the accretion is completely depleted. So it may be just born at some angle, or it may be true that it changes with time. So in Ecumen, actually, we see that in our 2018 observations, we see that it goes down to the 2002 value. So we know for sure it changes with time. So it's a not static situation. That is the only thing that we know for sure. But as I said, one model that I like is the pushing by accretion stream, the accretion disk. But nothing for sure.
All right, any more questions here? Let's see, any questions on Zoom? Let me see if there's anyone raising their hands on Zoom. People can hear us on Zoom. No. No questions on Zoom. Okay, then let's thank our speaker again. Thank you, Krystian. Thank you, and I like the advertisement, so students might see the recording and come to you. Okay, hopefully I'll see you next week. Then. I'll give you this.